screen. If you don't worry. We'll just get the model that we arrived at in class on Wednesday, and then we'll take it from there. And then we'll all generate the model of the card deals from last time. This is related to the quiz on Wednesday. So if you're looking at the quiz and not really understanding what the connection is, you'll see it after the first, say, next 30 minutes together. Okay? So these are the folks, 289 of you started flipping coins, and these numbers here represent the number of people that took this many flips to get heads. So 289 of you started with 0 flips. After 1 flip, 132 of you were out, if that makes sense. 132 of you, because it took until, if you think about it as being done, 132 of you flipped heads on the first flip. So that means the remainder would be whoever's still flipping, if you think about it that way. It took 75 people 2, it took 38 people 3, and so forth and so on and so forth and so on. We kept going until, I think it was only one person had 9. Do you notice how there's a data point missing between 7 and 9? Do you remember why?
0.
There was a 0 there. Why was that bad?
Exponential.
When you have an exponential model, you can't generate a 0 y value. We had a nice long discussion about that on Wednesday. In case you need to go back and review the last, I talked about the last video of class, and we'll walk you through that again. You can't zero out. We kept zooming and zooming and zooming in on that graph. That beautiful, which I think is still in there. No, I turned it off. We'll have to get that graph back. I'm going to get the scatter plot back on. I had to turn it off because of 243. Here we go. That's beautiful. Little zoom stat. There it is. There's our data. Coming down like this. And notice how it looks like it's hitting the x-axis. Is it? And Gary's saying, no, it's not. And we proved that it wasn't after we found the model. I'm going to find the model again. Okay. And if this is going too fast, again, don't worry. We're going to do a couple different models here in a minute. It was an exponential model. We liked that one. Stick it in y1. Beautiful. Boom. There she comes. Here she is. Ha, 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 ha. It looks like it's hitting the x-axis. We kept zooming though. We used our new friend Zoom Box, Z-Box, and we kept going in and looking and going, and no matter how close we got, there was always this shape in the window. When we zoomed in over here, it went like this, meaning that even down here, when you zoom in close enough, it still has a curve to it. It's still trying to get down but can't quite get there. And if you can zoom in again, and it still has the same shape, and you can zoom in again, and it still has this, and so forth and so on. So it never zeroes out, but it just gets super close. This is also related. I was thinking about making a quiz for you guys on the half-life of drugs. I might do this for you. We'll see how time goes. And I think it is, okay, there's one book for it's cool. When you take a drug, like ibuprofen, for example, it's got a half-life, meaning the time it takes for half of it to go away. Time it takes for half of it to go away. I think it's 4 hours, or maybe 8 hours on ibuprofen. I forget which. 4 to 6? We'll call it 5 then.
C.
C, bueno. So 5 hours, half the drug is gone. So you take 100 milligrams. Well, let's go back to this. When I injured my shoulder, my doc said take, how many was it? No, it was 6 more than the usual amount. 6 pills, which would be like 1,200 milligrams.
Yeah, you do 3 or 2, but you do 6 is the most.
And 6 is, they're 200 milligrams a pop, I think, yeah?
Yes.
I'm going by memory here. He had me taking 50% more than the maximum that's recommended on the bottle, and it freaked me out because I've heard people getting upset stomachs and like stomach tear linings from taking too many. He's like, for 2 weeks it won't kill you. So I take 1,200 milligrams of ibuprofen. I've had Advil. 5 hours later, how much is left in my body? 600. Half of it's gone. 5 hours after that, how much is left in my body? 300. 5 hours after that? 5 hours after that? 5 hours after that?
32.5.
Close, 37 and a half. 5 hours after that? We'll call it 18. Make the numbers nice now. 5 hours after that?
You need more.
9. Well, we need more. Good. But what I'm saying is the initial dose is still in my body. And no matter how far out I go, will it ever go to 0? No. Right? Think about it. You're losing half every 5 hours. Good. I'm going to make this quiz. This is going to be a good quiz. Every 5 hours, you're losing half of what's remaining. But you're never getting to 0. You're rounding to 0 eventually. Eventually. So we're at 18, yes? 5 more hours, we're at 9. 5 more hours, 4.5. 5 more hours, just about 2. Make it 2 to make the math easy. 5 more hours, 5 more hours, a half. 5 more hours, a quarter. 5 more hours, an eighth. 5 more hours, a 16th. It's never going to go to 0. But it goes to 0 enough. It gets close enough to 0 that you then eventually have to take more drug to sit on top of that. But this is what you got to think about. Mathematically, the aspirin you took when you were 9 is still in your body somewhere.
That's what I was just going to ask.
Isn't that wild?
That's kind of creepy. I don't know why
It's creepy, but it's also mathematically negligible. That's the idea. It's mathematically negligible because it's such a small amount. At this point, it's 0.000000000000001. And I probably didn't have enough zeros there. So all those little amounts do add up, though. And that's one of the arguments I've read over and over about the over-drugged society, is that all those little tiny... You've seen Office Space? When they create the algorithm for setting the fractions of a cent to themselves, and very quickly they become multimillionaires, all those little fractions. The argument medically is that we're over-drugging ourselves, and so much of those little fractions are adding together. Now, you'd have to take an insane amount of ibuprofen over an insane long period of time to have that mathematically add up. So it's 0 enough. It's getting close, but it's never actually touching it. You've heard of some drugs that are resident in your spine, resident in your body for a long period of time. Every drug is like that. It's just that so many of them fall away so quickly that they get to a fraction that's ignorable pretty fast, like over the course of a day. Fair enough? Good. Oh, this is going to be good. I'm going to remind me at break. Somebody remind me, just Half-Life quiz, and I'll send myself an email and make a quiz about that, because it sounds like you guys are interested in that. You can ignore it, of course, if you want to, but those of you that are into it can do the quiz, and you might learn something from it, because it's tied to this, believe it or not. This is a drug curve. I mean, literally, this is a drug curve. If you think about it. What I want to do right now is analyze that curve. I want to back out to the model. This is as far as we got on Wednesday. Y equals, that's the general form. Y equals a times b to the x power. So the equation, if you plug those numbers into it, is y equals a, which we'll call that 267, times 0.53, we'll round up to 2 decimal places, just you'll see why momentarily, to the x power. We can turn this off momentarily because we don't need it right now. And I want to focus just on that. Wait, what's the matter?
Nothing.
Oh, no, okay. I'm terrified there for a second.
Sorry.
I don't want to terrify people any more than I already do. Now, I want to focus on these numbers right now and how they tie into what you guys were doing in class. And then we're going to move over to the other group with the cards and see how a similar equation should tie in. And then when you do the quiz, if you choose to do the quiz for Wednesday, you'll see how that ties in too. It's all the same pattern. It's all exponential. What does the 267 have to do with? What do you think it has to do with?
267 of the...
Oh, okay, good. What mathematical purpose does the 267 serve in that equation? What is it? It's actually something you know the name of. You know what it's called, but you've never seen it in this form before. Maybe we'll turn the curve back on so you can see it. It's here. Less angle, more just pure number. I like that idea though. I'm going to clean up the graph a little smidge, guys. Go to 10, x scale of 1. Make that 0. Make this something more logical, like 300. Make it by 30. There. Okay. So this is 0, 30, 60, 90, 120, 150, 180, 210, 240, 270, and 300. Do you see where the curve is coming in? And then, so what's that?
Where we start?
Give me the mathematics. I love what you're saying over here. I love what I'm hearing. It's perfect. Give me the mathematics of what it is. It's the blank blank. It's the y-intercept. Thank you. Good. It's the y-intercept. Good. Like, oh my god, okay. Perfect. Good. Now, why is it the y-intercept? YWHY is it the letter y-intercept? Mathematically, I'm not forgetting what you guys said over here. It's perfect. I want to get back to it. But mathematically, why is that where the curve hits the y-axis? Please, Lisa.
It's where it's intersecting through the line. It's going through the y.
Good. So if it's going through the y-axis, what's x?
0.
If it's nice. If it's passing through the y-axis, that means x equals 0. Remember we said earlier you can't have y equals 0? You totally can have x equals 0, and this is how come. I'm going to say y's. This is the reason how come you can have x equals 0. If you let x equal 0 in this equation, x is 0. What's 0.53 to the 0 power?
1.
Okay, we've got some dissension. Half of you are saying 0, half of you are saying 1. Maybe we should call it a half and call it good. No. Let's figure out what it is. Because this is a question on the quiz, too. that was thrown to before. I've got some emails over the weekend about this. I want to make sure we get an answer. Swing over to this board briefly. I want to talk about what happens when you raise